Can we all agree on measuring the length of something? It turns out that we can't. Let's look at the idea of length contraction. We've seen that time passes differently for different observers. This should give us the hint that lengths and distances must also be somehow affected by motion because space and time are always interlinked. Just think of the definition of speed. It is distance divided by time. So if time behaves in a strange way, then it should not be surprising that distance does too. We're going to use the ideas of special relativity, and in the same way that we looked at time, we're going to see how two people measure the length of a body when one of them is moving and the other is not. This time, Alice is on a train and the train is moving at constant velocity past a stationary Ben. So both Alice and Ben are inertial observers. What we're going to do is see what Alice and Ben measure for the length of the train from their perspectives. Alice is in the train and it is moving at constant velocity. So according to relativity, she can claim to be at rest in her frame of reference. Since the train is not moving with respect to Alice, it is simple for Alice to measure the length of the train. She can just take a tape measure and see what the reading is for the length of the train. We will call this measurement LA. This is the length of the train that Alice measures. When it comes to Ben measuring the train, however, it is not so simple. Ben cannot use a tape measure because the train is moving past him at a velocity v, so there is no way that Ben can take a physical measurement of the length of the train. So what Ben decides to do is to use a stopwatch, and he ensures that he starts the stopwatch exactly when the front of the train passes him, and he stops the stopwatch when the back of the train passes him. In this way, Ben can work out how long the train took to pass him going at velocity v, and we call this time TB. Since we know that distance is velocity times time, we can say that Ben measures the length of the train to be LB, and this will equal V times TB. Now, we've already seen in the time dilation video that the passage of time TB for a stationary Ben was related to the passage of time for a moving Alice by this expression. Now, in our case, for measuring lengths, it is actually simpler for subtle reasons that we won't go into here if we regard Alice as being at rest. Now, we know that Alice can do this because she is an inertial observer, so she can claim to be at rest and say that Ben is moving past her. So we will let Alice claim she is at rest, and so is the train, and both are in the same frame of reference. And so the passage of time for Alice can then be written as this. We can now take the expression for the passage of time for Alice and rearrange it to give us the passage of time for Ben. This may seem a bit long-winded and a bit circular. You might say, why didn't we just start with the time for Ben anyway, with him being at rest? And the answer is we could have done that, but the procedure which follows that approach is a bit less easy to follow. So for the sake of simplicity, what we have done is to start with Alice being the one claiming to be at rest and then take things from there. So we have this time for Ben, and we've already seen that the length of the train that Ben measures is given by LB, which equals V times TB. In this length expression, there is a TB, and so we can use the expression above for TB and substitute it. And we get this expression for LB, the length of the train as measured by Ben. We note, however, that we can also say that V times TA is going to be the length LA that Alice measures for her train. So our expression for LB becomes this. We note that the square root part of this equation is always less than 1 because Alice's speed v cannot exceed the light speed. If we look at what happens at different speeds, then when V equals 0, LB equals LA. This is what we would expect. If Alice and the train are not moving, then both Alice and Ben can measure the length of the static train and agree on the answer. But if V equals c, the speed of light, then V upon c will be 1, and so LB equals 0. That is, Ben measures the train to have a 0 length. This can never happen, of course, in real life, because no physical object can ever reach the speed of light. So this case of V equals c is just the mathematical limit of this expression. It cannot be real. So now we can see clearly that LB is always less than LA, which means that Ben always measures the train length to be shorter than what Alice measures. This is relativistic length contraction. There is one other aspect to this. The length contraction only happens along the direction of motion. So the height of the train will be the same for both Alice and Ben, because the train is not moving in the vertical direction. But along the direction of motion, Ben and Alice will not agree on the length of the train. To Ben, the train will appear to be compressing horizontally, and the closer the train gets to the speed of light, then the thinner the train will appear to Ben. So this is length contraction, how a moving body appears shorter to an external observer. As with time dilation, the effects of length contraction are just not noticeable enough in our everyday lives for us to experience them, because the speeds we experience are just too small compared with light speed. If we take an example of the fastest fighter jet, it can travel at typically 2,500 kilometers per hour, so much faster than anything else we would see on Earth. And if Alice was flying this fighter jet and Ben measured its length from the ground, Ben would only see a length difference of about 53 nanometers. That is only about 1,000 hydrogen atoms. This difference in length is inconceivably small, and this is why none of us can see length contraction effects in daily lives. But just like time dilation, length contraction is real. So there we have it. Special relativity shows us that time and space are not absolute or fixed. How we experience them depends on how we are moving. They're personal to us. I hope you have managed to follow along with the strange concepts of time slowing down and lengths becoming shorter. Relativity is strange, but this is how the universe works. We will look at some more relativity ideas soon, so until then, keep thinking physics.